Hi, folks. Yeah, as you can tell from my accent, I'm from Los Angeles originally. Who here climbed the stairs to get up to this room? Keep your hands up if you took public transport to get to USC campus. Wow. I didn't manage that. All right, great. What I'm going to talk about today is serverless for data scientists, and we're going to talk about data science about halfway through the talk for the rest of the talk. The first half is going to feel like DevOps, and that's like necessary eating of your greens that you have to do to get to the good data science stuff. So if you're worried halfway through that this seems kind of weird, don't leave. Data science is coming. This could have been a 90-minute tutorial where we do stuff interactively, and rather than do that, I've put all the code on GitHub. So by all means, try and follow what I'm saying as well as you can, but you do have the luxury of checking this stuff out after the talk. So let's get started. These are computers, and I think it's generally agreed that these things were a bad idea. One of the great things about the cloud is it allows you to put the hardware, at least, in a sort of a notional trash can of your mind, if you like. By moving to the cloud, the hardware becomes somebody else's problem. The power, the air conditioning, swapping out broken hard drives, all that is someone else's problem. And the usual suspects, Amazon, Microsoft, Google, do such a good job of that you can effectively forget that the hardware exists. Modulo that bit at the start of any project where you choose, am I going to use like a P2X large or a T2 micro or whatever. You can pretty much forget the hardware apart from that. There are a couple of problems with moving to the cloud, though. This is one of them. It turns out to be, on average, a fairly efficient way of setting fire to money, and there are exceptions, and kind of one of the themes of this talk is a way of using the cloud inexpensively, but generally speaking, this is true, and the reason it's true is, in the move to the cloud, or even if you do stuff on your own hardware, you necessarily set up long-running, large services that have headroom, that have room to grow as your needs grow, and what that means is you're not running at 100% utilization, you are necessarily burning dollars for unused CPU time. The other aspect, the other thing that remains a problem when you move to the cloud, and again, this is equally true on premises installations, is this. This is recent footage of me configuring, maintaining, and securing an operating system. This is not my job. I'm not good at it. It's not something particularly I like to do. And I think most importantly, it's not how my company makes money by me doing this. So I'd love to stop doing it. I'd love to live in a world where not only the hardware goes in sort of a notional trash can, but also the operating system, the container technology, all that nonsense, I can forget about it and focus solely on the business logic of what I need to do, the application layer. That is the claim, at least, of serverless. That's its goal. So let's take a second to sort of define one way of thinking about what serverless is. So imagine I've got an idea for a business. I've got a new unicorn startup idea. What I want to do is provide an API that adds two numbers together, and I believe I'm going to be the next Slack if I do this. So business is going well already. I've got my first request, and in it comes, and someone wants to know what's 2 plus 2. In a serverless deployment, what happens is some kind of long-lived gateway service summons out of thin air a server. That server performs this computation, and those of you who've had your coffee will already have figured out what the answer is. And then, crucially, this is the defining aspect of serverless, that server goes out of existence. It was summoned into existence not to perform this service generally, but to perform this service for that single function call. So business is going really well now, and along comes another request, and the same thing happens. My gateway service summons out thin air some hardware to perform the computation, and then that piece of hardware dies a noble death. It's as though it's never existed. What you'll note here is between these two calls to my API, I had no infrastructure. And it's in that sense that this is a serverless deployment. The servers are created only as and when they're needed. For those of you who are like hardcore data scientists who know what Bayesian non-parametrics is, you know that's a terrible name because non-parametrics actually means lots of parameters. Serverless is kind of the same deal. In practice, serverless is used in situations where we don't get 2 API calls over the 3 minutes it took me to explain that slide. It's when we get lots of API calls. But the point is our infrastructure scales up linearly with the amount we're using it. And crucially, that linear relationship, again, for the data scientist in the room, has an intercept of 0 or very close to 0. We do not pay for our infrastructure when we're not using it. So given that we want to forget about operating systems and hardware and stuff, this is a nice story, but clearly we'd like to pay someone else to solve all the technical details that enable us to work as data scientists or operations people to work in this way. And that's where these folks come in. So AWS Lambda is perhaps the best known serverless platform. Google Cloud has functions, Azure has functions. And then if you feel very strongly about the details of your deployment, or you've got someone else to take care of the problems that come with it for you, there are open source, like roll your own implementations of serverless, and OpenFaaS is one of the better known ones, but certainly not the only one. Throughout this talk, I'm going to be using AWS Lambda. I think it's the most mature, certainly, and a lot of the tools I'm going to be using are targeted at it for now. Let's actually do something with serverless, and this is where you might be worried that I'm not actually going to talk about data science. This is a web application. This is a Flask application. For those of you who haven't seen Flask before, don't worry about most of the details. Just look at that function in the middle, that function time. Hopefully it's obvious what time is doing. Time is returning a string that gives the current time. No one's going to win a Turing Award for this, but we'd like to deploy it. So I'm going to make it a Flask application. The way you wire a Flask application together is you use one of these decorators, which is the line immediately before the function definition, that says to Flask, if a request comes into yourwebsite.com/time, give the user the return value of that function. And obviously for like an interesting web application, that would be some HTML with some templates and stuff like that. But we're just going to return the time. So how do we deploy this? This is what a local deployment of this application looks like. I just run python app.py, and Flask very helpfully tells me at the end there the URL I can find it at, which is localhost port 5000. And then if I visit that URL, I could do this in the browser, but just for this slide, it's here with a curl command. I get the time, and apparently I was writing this talk at 9 at night a couple of months ago. So that's all great, but obviously I have aspirations to close the lid on my laptop at some point. I also don't want to deal with the security implications of serving a web application as a long-running service. So I'd like to deploy this in the more formal sense. So let's do that using serverless. And one of the nice things we'll see is this turns out to be relatively cheap. So how do we actually do this? Deploying a web application on serverless involves a tremendous amount of clicking around in the AWS console, and I don't recommend it. What I recommend you do instead is use a command line tool, and there are 3 that I know about. Zapper is the one we're going to be using in this talk. Chalice is AWS's official equivalent that only works with AWS Lambda. Zapper, at least in principle, is agnostic about which serverless backend you're using. And then, confusingly, there is a node option called Serverless, which is not a great name for something, but officially it's called the Serverless Framework. You'll hear it called Serverless, and like I say, it requires you to use the Node Package Manager, which is, most of us don't have time for that. So we're going to use Zapper for this talk. The first thing to note, and I'd say this at a data science conference, is you have to use virtual environments. You can't use Anaconda distributions for this. You're going to have to define locally and create locally a virtual environment to deploy this application. So before this slide, I created a virtual environment. On the second line there, I'm going to activate it and pip install the one dependency of this web application, which is Flask. And then I'm going to run Zapper init. And that is Zapper's way of gathering the information it needs to deploy the application. What you're not seeing here off the screen is 5 or 6 questions that I get asked. And in fact, because this application is so simple, configuring it consists of hitting enter 6 times. So it's not rocket science. And you can tell it's like a nice, cool tool because there's ASCII art right at the start. And once it's done, what you've got written to disk is this file. This is a configuration file that tells Zapper how to deploy this thing. And most of this is boilerplate. The only interesting thing here is the first configuration entry app function. That app.app there is telling AWS Lambda, or Zapper and then AWS Lambda, that when a request comes into this service, the Python object you want to use to service that request is the object app in the file app.py, which was that Flask application I showed you a couple of slides ago. So we've configured things, but now we actually want to deploy it, and it may not surprise you to learn that the command to do that is Zapper deploy. And here's all the stuff we could be clicking in the console if we hated ourselves. There's a lot of stuff to do here. But the good news is it's all taken care of. If I were doing this live, I think this takes maybe 30 seconds. And you can do a Zapper update, which takes less time if you make a change to your application and not your dependencies. But the important thing is right at the end here, there's a publicly accessible URL. And I think if any of you want to know what the time is right now, if you type that URL in really quickly, you'll get the time. or I can tell you if you want at the time. But the important thing, like I say, is most of this stuff, it's wonderful not to have to worry about it. One thing I want to just draw a little bit of attention to is that line, fourth line down, packaging project as zip. That's what Zapper does for us. It packages up our application and its dependencies in a zip file, which is the thing that gets uploaded to AWS. It takes care of that for us. And the reason it's able to infer dependencies is its definition of dependencies is everything it finds in the virtual environment. So don't install Notebook, don't install SciPy if you don't need it in these virtual environments. Keep them nice and clean, because that's the thing that's going to get uploaded to AWS. And once we've done that, we can curl this URL and get the time. And apparently it was 4:30 in the morning when I was writing this talk. It wasn't really, that's UT at 9:30 at night in the Pacific time zone. So that's AWS server time zones there. If you're interested, on the GitHub, there's some more code to show how you take URL parameters, how you handle time zones, all that sort of stuff for a slightly more complicated web application. But we're now going to move on to a second use case that serverless is great at, which is cron jobs. For those of you who don't know, cron jobs are recurring tasks, things that recur at a set time each day, a set number of times each month or each year or whatever. This is things like defragment my hard drive, download this URL, these sorts of bookkeeping tasks. I built a cron job that is this Twitter bot. If you follow on Twitter, DWXDTLA, that's changing weather in downtown LA. And it's just a bot that tweets the weather every morning at 7:30. And I don't actually know what a Fahrenheit is, so I added a function to it that tells me if it's warmer than yesterday or colder than yesterday. That's my great innovation for 2018. There are two of these bots. There's one for New York City as well. This is all done by serverless. I pay less than $0.01 a month for this to happen, 60 times a month for the two bots. The configuration file to get Zapper to deploy this ends up being a little bit more complicated. I had to write this one by hand a little more. But I just want to highlight two additions from the last one we saw. One, the expression thing there is essentially a cron tab line. If you've used cron on a Unix system before, this is a thing saying do it every hour on the half hour. And then the second big block of of configuration there is the environment variables. That's where I can inject application-specific configuration. In this case, the latitude of the place that I want the Twitter bot to post the weather for, and my passwords and things like that. So that's all wonderful. And of course, the reason it's wonderful is money. But I want to talk about a couple of other reasons why, if you talk to operations people, some of them really like serverless. One is we are able to focus on business logic. Apart from using analogies like cron jobs there, I didn't really talk about Unix in any way. We were able to focus mostly on business logic. Additionally, and we didn't really see it because I've got 2 Twitter bots, not a billion Twitter bots, but additionally we're getting scalability, essentially infinite scalability built into the application the second we deploy it. And obviously we're going to pay for that if we end up with an infinite number of users. But we do at least have the scope to grow immediately without thinking about scaling out or any of that sort of stuff. But the advantage that interests me at least is this one, it's money. And that's because we're only paying for our code while it's running. Those cron jobs cost me 0, essentially. I believe Amazon rounds to the nearest cent, which means I think they do actually cost me 0. And then the web application is only going to cost me what I get in terms of users. So if my time service is successful, then good for me, and it's going to cost me a little bit of money. We'll dig into what these cost savings mean for data science in a second, but I want you to hold them in your mind. Here's an example from the operations community of a big financial savings. This is the readability API. If you know Instapaper, readability is a bit like Instapaper. So you take in a rich web page full of headings and adverts and pull quotes and media and stuff like that. And you give the URL to the readability API, and it gives you back the plain text version of the web page to display in a reader-friendly format. And then the economics of the media industry collapses. But it's a wonderful service. And they used to pay $10,000 a month to run this on EC2 instance. They migrated to serverless, and now it costs them $370 a month. So $10,000 to $370 a month is a big saving. Now, it's not all sweetness and light. It's not all good news. There are a couple of problems. 2 of them are sort of disadvantages that are in the nature of serverless to the extent it's like microservices. Microservices is a way of deploying a relatively complex application, and serverless shares some of its characteristics. And one of the criticisms you'll hear of microservices is that they tend to be complicated. They tend to have a large surface area internally to the application, and that can make debugging tricky, just as a practical matter. The other disadvantage of serverless that I want to acknowledge at least, but is not going to bother us for most of the rest of this talk, is vendor lock-in. I can't take this application, if it's a moderately complicated one, and just SCP it from AWS Lambda to Google Cloud. It doesn't work like that. And that vendor lock-in can be vicious for interestingly sized applications. And it's something, if you're thinking of doing something at a reasonable scale, it's a real concern that you should consider. But the disadvantage that is more interesting from the point of view of the rest of this talk is this one. And this is not so much a disadvantage as the point, the premise of serverless. These machines that are summoned out of thin air, we haven't talked much about what they are. They are real sort of logical machines, containers or something running on AWS hardware. I like to think I know a reasonable amount of about serverless, and I don't know much about these machines, and that's a measure of the success of the abstraction. But they are machines, and they are actually quite under-resourced machines. They're not quite as under-resourced as this picture, but there is a hard upper limit right now, I think, of 1.5 gigabytes of RAM on an AWS Lambda instance. There is a hard upper limit that the function has to return within 300 seconds, and that was increased to 15 minutes, which is 900 seconds. So that limit is going up, but it's a limit nonetheless. So if you've got an interesting sized data science-y computation that takes 20 minutes rather than 15 minutes, you're out of luck for serverless. So that's a real thing to consider. So these things are underpowered machines on borrowed time. And those constants I mentioned, 1.5 gig, 3 minutes, 5 minutes, 15 minutes, they're all likely to change. Since I first gave this talk, the 5-minute went to 15-minute limit. And if you go to Google Cloud or Azure, they're different numbers. And if you roll your own and install it on your own hardware with OpenFast, you can choose whatever those numbers are for your use case. But the fundamental idea that these are machines that pop out of existence once they've run the function is the point of serverless. And what that means is it kind of restricts the kinds of functions you write. On their own, these functions have no way to remember what happened the last time they were called. They also have no way to communicate with other functions running at the same time. You can, I was going to say hack that in. It's not really a hack, it's how people do it. But you can call out to databases. You can have side effects like posting to Twitter. So they're not truly pure functions in that sense. But it does change the way you think a little bit about programming. So, finally, we're getting to the data science bit, and here's a picture of data science. We've got these machines that have no internal state. They're not very fast either. But the important thing is, potentially, we've got a very, very large number of them. And we can summon them out of into existence and out of existence effectively instantly and only pay for them while we're using them, which raises a really, really interesting possibility for data science use cases. So if you get one thing from this talk, I would love for you to read this paper. This is an academic paper, but it's a relatively accessible academic paper. And it introduces a tool called Pyren, which is what we're going to talk about in the rest of the talk, is like how you actually hands-on keyboard use Pyren. But I think this is also an interesting piece of research and sort of a polemic about how we can do distributed computing when not everyone works at Twitter and Google and Facebook. Like I say, this is the paper that introduces Pyren. And Pyren is a tool that maps functions across parameters using AWS Lambda as the computational backend. So let's first look at what I mean by maps functions across parameters without using AWS Lambda. I'm going to map functions across parameters on my own laptop here. So here's my function. This is square. So it takes a number x and it returns its square. I would like to map that across some parameters, in this case the numbers 0 to 5 inclusive. And the usual Python way of doing that is with a list comprehension. So this is going to give me 0 squared, 1 squared, 2 squared, and so on. The sort of Haskell nerd way of doing the same thing is with the map function. The map function, as of Python 3, does not directly give you back the answer. It gives you this map object, which is sort of has the possibility of giving you the answer if you call list on it. It's a generator. This is complete sidebar to the rest of the talk, but the reason I'm emphasizing Python 3 here is you're at a PyData conference. You should all be on Python 3 now, because a little library you might have heard of called NumPy is dropping support for new versions of Python 3 in January 2019, which I used to think was like the space age, but Python 2.7. What did I say?
You said 3.
That would be a very aggressive timeline, wouldn't it? They're dropping, so yeah, everyone leaves the talk immediately. So they're dropping support for Python, new versions of Python 2. starting in January, which I used to think was like the far future, but it turns out that's like 10 weeks away. So you should all be on Python 3 now, and ideally Python 4 apparently. The point is, this is how you do it on your own machine. Let's say I've got a really old laptop, and I do actually have quite an old laptop, and I'm worried about its ability to compute these 6 calculations, these 6 square numbers. I'm going to shift the computation now to 6 AWS Lambda instances using Pyren. So here's how you use Pyren. Import Pyren, then you create this executor object. And the significance of the executor object is that it has a map method that is API compatible with Python's map function. So it takes as arguments the function you want to map and the parameters you want to map them across. Again, just like Python 3's built-in map function, it doesn't give you the answer. It gives you something that allows you to get the answer. And in Pyren's case, it's going to give you a list of futures objects. And you can call result on these futures objects and get the result back and accumulate all the results there. So that's very nice. I'm not live coding now, and if I were, you'd see a frankly rather alarming amount of time it took to do this. This takes about 20 seconds, just hit return 5 times here. And it takes the time when you call the result method, when it accumulates the answers. So let me put my cards on the table and show you what's going on here. This is a plot of the time taken by these 6 workers that do this computation. The workers are each a row on the plot, and then the x-axis is time. And if you can't read the scale of the x-axis, the upper limit of the x-axis is 20 seconds. So this whole thing took 20 seconds to take the square of 6 numbers, which is not a win computationally. But I want to break down what's going on, and then we'll talk about some use cases where it is a big win. So what is Pyren doing to use Lambda as the back end? First, the blue dots correspond to host submit. And what that means is package up your application and upload it to AWS. And in fact, the place it uploads it to, it may not surprise you, is S3. Then task start means summon into existence 6 AWS Lambda workers, which then ask this S3 bucket for the application. And additionally, in this case, they install an Anaconda runtime. So the people who built Pyren are very much focused on users like you and me, who all need the same set of like 10 libraries: NumPy, SciPy, scikit-learn. I don't think there's a deep learning library in there, which is fine because there's no GPUs on Lambda. But this sort of set of this data science ecosystem is installed. So if you want to do something different, Pyren may not be for you. If you feel strongly about version numbers, Pyren may not be for you. But for now, installing an Anaconda runtime is great, because it means we don't get in a mess with like Fortran compilers on AWS Lambda, which is no fun. So the application is now on these AWS Lambda instances, and the runtime necessary to do the calculation. That's setup done. The computation is performed, that's task done, and results returned is the bit where my client, in this case the laptop, calls that result method. And you can see those results are staggered there, and that's the latency of my internet connection. That's the global interpreter lock, and each one taking a second for me to pull down. So this whole thing adds an overhead, a huge overhead of like 20 seconds. So don't use AWS Lambda, don't use Pyren to do things that take less than 20 seconds. They have to be in kind of a sweet spot, which is now from like 20 seconds to 15 minutes, there's quite a lot of stuff we do day to day that's in there. And I'll show you how to move stuff into that domain as well for a speed up in a second. But one thing I just want to note about Pyren, don't actually do this, but this emphasizes Pyren is a drop-in replacement for the map function potentially. If you wanted to globally change all the maps in your application to use Pyren instead of your own computer, you could run this at the start and just overwrite the map function. And that sort of shows off that Pyren is compatible, and also that Python is like a dangerously dynamic language where I can rewrite the standard library at runtime. Why would I do this, or why wouldn't I do this? I would do this, I would benefit from Pyren if the things being mapped, the computations being mapped, are embarrassingly parallel. That's the use case that Pyren serves. So we need to define embarrassingly parallel, and this is our third and final use case for serverless. So what is embarrassingly parallel? This is a field of carrots. We would like to harvest these carrots. If we've got one tractor, we've got 80 carrots here, 8 rows of 10 carrots. And this tractor can farm the carrots at 1 carrot per second. This tractor is clearly going to take 80 seconds to complete this field. If we are willing to pay for a second tractor, we can get this field done in 40 seconds. And if we're willing to pay for 8 tractors, we can get the whole thing done in 10 seconds. We're getting a linear speed up as a function of the number of tractors we've got. And the reason for that is that the tractors operate independently. They don't need to talk to each other, say, can I look at your carrot before I pick up this carrot? It's a totally independent operation. That's in contrast to, let's say, 2 people who agree to write a book together. They need to coordinate. One person needs to write one chapter because it affects another chapter. So they need to work kind of in series rather than in parallel. Embarrassingly parallel is this kind of extreme parallelism where no communication is required between the workers. Taking the square of 6 numbers is embarrassingly parallel. The naive implementation of the algorithm to do the square of lots of numbers, you do not need to know the square of 2 in order to compute the square of 3. There are actually speed-ups if you do know that, but the naive version is embarrassingly parallel. So we're looking for things that are embarrassingly parallel and in that sweet spot of taking somewhere above 20 seconds and below 15 minutes. So here's a real example of this from my own work. So like there's this old canard about data science that you spend most of your time preparing data and getting data rather than training, recurrent neural networks. And that's, normally my job is to train recurrent neural networks, and it's true for me as well. So I wanted to get all the abstracts from NIPS. NIPS is a machine learning conference. It was in Long Beach last year, and it's hell on earth if you ever get the chance to go. So I recommend you run this code rather than go. So you'll get the abstracts. And if you're interested in either the abstracts or the code, then there's a GitHub link there. Scrape batch here is the function we're going to map across parameters, and the parameters are going to be batches of URLs. You might think, write a function to scrape one URL and map it across a list of URLs. But instead, I'm going to write a function to scrape batches and map it across a list of batches. And the batches are like 100 papers long. And that is to get me well into that sweet spot where AWS, Lambda, and Pyren are worth it. If I scrape a single URL, it's going to take 5 seconds or something like that with the startup latency and stuff like that, which on top of the 20 seconds is not a big win. If I start scraping batches, then I get 2 big effects. One is, if I do this locally on my laptop, I'm constrained by the global interpreter lock or the number of cores on my machine or something that constrains the number of URLs I can simultaneously scrape or the number of jobs I can simultaneously run to be a number like 4. Maybe if I'm clever and I do it asynchronously, I can increase that number. But it's going to be an order of a few and maybe even 1. If I use Pyren, I can do arbitrarily many at the same time. I can do 256, I can do 1,024, I can do whatever I want. The other big advantage of doing web scraping on AWS, it turns out that the AWS, the organization, those data centers have a slightly faster connection to the internet than Time Warner is able to provide me in my home. So we get this big speed up, and the speed up, I think I went from doing this in like 30 minutes on my own machine and like overloading my internet connection and Netflix doesn't work and all that stuff, to doing it, I think it took 3 minutes. So it's not gone down to 0, but it's a big, big speed up. Let me show you a more substantial speed up and a more substantial numerical calculation. This is not my work. If you go to Bradford Lynch's website, you can see the details. Black-Scholes is a differential equation that describes the evolution of the price of the instruments on the stock market. In practice, famously, it fails to describe the evolution of the price, but solving it 305 million times is a totally reasonable thing to want to do. Let's say you wanted to prove that it doesn't work. And that's a fairly substantial calculation, each one, and each one is embarrassingly parallel. These are independent time series, or in theory, they're independent time series. The speed up Bradford Lynch got, you might not be able to see it right there, 270x. And crucially, when this was all done, he had no infrastructure left. He wasn't left with some huge GPU machine under his desk that he's paying through the nose for air conditioning for. He didn't have to go and talk to data engineers or IT to set up a Spark cluster. This was all done by hitting return from a Jupyter notebook. The infrastructure required sprung into existence and then ceased to be when the job had finished. I've also seen people take this approach to like long-lived data engineering tasks, things like video encoding, which is embarrassingly parallel in certain forms. Like you can encode, if you're using an encoding algorithm that encodes 1 frame at a time, that's obviously embarrassingly parallel. And that kind of long-lived job can scale up or scale down as the amount of video you need to encode increases or decreases, importantly. And that's really cool. But the use case that interests me most is this Pyren use case. And the reason I think serverless is a particular interest for that Pyren type use case is it's great that we can scale it up. But one of the important things we know about data science is we spend a lot of time like drinking coffee and sleeping and not running these big computations. So the ability to scale down our infrastructure to 0 and not pay for it is particularly compelling. To not have a Spark cluster sitting there burning money while we try and figure out why the dimensions of these arrays are backwards or something like that. It's a big, big advantage, I think. So finally, I want to tie together the first and last use cases. This is kind of the party trick at the end of the talk. This is hyperparameter optimization, which is embarrassingly parallel, and then deploying a model on AWS Lambda using Zapper. This is a good fit for both these tools, and we'll see why in a second. So here we've got some training data. This is, apparently I want to tell the difference between the yellow blobs and the purple blobs based on these two features. We've got features that run from like 0 to 10, and then from like 4 to 12. And the yellow is on the left, and the purple's on the right. If we wanted to train a model to do this locally with scikit-learn, we'd probably write some code a little bit like this. So we've got a k-nearest neighbors classifier. That's kind of the simplest thing you can do, and it'll do for our purposes, and I hope you can sort of extrapolate out to more interesting size machine learning problems. And we instantiate the classifier, we fit it, and we score it, and we get 83.8%, which is pretty good, probably. The important thing to note here is there's a magic number. N neighbors is 5. That turns out to be the default in scikit-learn. That's the one I picked when I first ran it. But why isn't it 4? Why isn't it 6? Why isn't it 10? We need to try these possibilities. That's a hyperparameter search. And the right number will depend on our data. So I could do this on my laptop. This is not a large data set or a complicated machine learning problem. But to illustrate the point, I'm going to do that hyperparameter search using AWS Lambda and using Pyren. So remember, Pyren requires two things, a function and some data to map the function over. So we need to create those two things. So I should have put these two the other way around. Let's look at the function first at the bottom. This is a function that trains a model given some hyperparameters. So given one set of hyperparameters, it trains one model and returns the classifier, the trained classifier. We're going to map that function across these 8 choices of the hyperparameter. And it's just some Python nonsense, the double star hyperparams there is just to allow us to inject potentially more hyperparameters than just the one. So that is going to return a classifier, and we could map that locally using Python's map function, but instead I'm going to use Pyren. So I map it. Pyren has this utility function we haven't seen before, which is get all results, which you may be able to guess what that does. And we get back classifiers. An important thing to note here, when I previously showed you Pyren, it was giving you back very simple objects, things like just numbers, the square of 2 is 4, or it was giving you back text, like the text from a particular abstract page on NIBS. What's coming back here is our rich Python objects with data and behavior. These are scikit-learn classifiers that have been trained, that know the parameters they were trained with, that know how to score themselves on test data. Those rich objects survive the transition from S3 through this pickling and unpickling onto your client machine, which is, I think, like quite impressive engineering. But having got these hyperparameters back, we are able to score them. And so we can now look through the 8 possibilities, and we can find, well, 5 was pretty good. It was 83.8% accuracy. But we could have done slightly better. We could have had 84.2% accuracy if we'd have had nearest neighbors of 7. That obviously, if you've done any machine learning, is a trivial scale hyperparameter search. So I made it that way to be clear about what's going on with Pyren. But you can imagine easily doing more complicated things. The next thing I said I was going to do was serve this model. And before this talk, I uploaded a pickle file containing that best model, the model with 7 nearest neighbor of 7. I uploaded it to S3, and this is a Flask application that is going to serve predictions from this model. It's doing something really stupid here, which is necessary because we're going to deploy it on AWS Lambda. And that is each time the application runs, it downloads the model. And that probably seems quite inefficient to you. Why can't we? If we weren't deploying it on Lambda, we could keep this thing running and only download the model once. It is stupid. It is inefficient. It turns out the folks at AWS have made it less stupid than it should be by caching a lot of this stuff. I said these instances like kind of pop into and out of existence. That's kind of a lie. They keep them around. They keep them warm is the technical term they use for it, very technical. And what that means is some of this stuff is cached. And this is an example, and we'll see in a second when I hit this URL that it runs pretty quickly. The rest of the code is code to deal with Flask getting JSON in as input from the URL parameters, and then scikit-learn not really expecting JSON as its input, so we bundle some stuff up. And the API is going to give you back the string purple blob or yellow blob. So let's see it in action. This is the training data. Just to remind you, purple was on the left and yellow was on the right. And if I now go to the URL, what you're seeing there, you can see the URL parameters I'm using, or you probably can't. They're in the location bar. And I am using feature 1 is 3 and feature 2 is 6 there. So we're on the left-hand side of the image, so we're getting purple correctly. And now if I can do this, I'm going to change feature 1 to 9, and look at that, machine learning in production. So we were able to do all that without talking to data engineering or to IT or getting anyone's help. This is what you as a data scientist can now do using tools like this. So, right. So I want to sum up finally by saying what serverless is good for. Like, that may have seemed kind of an incoherent grab bag of stuff. And I want to draw some themes so you can spot patterns in your own work that might be a good fit for this. We saw it was good for web ops. It's able to scale up to very large usage. You know, your unicorn goes well, or you don't get any users. It is able to do cron jobs, which are clearly, you know, very sort of atomic, potentially quite short-lived tasks that most of the time don't run. And then it's able to do, we saw at length, embarrassingly parallel computation using PyRen. These three things have in common that they're bursty. They potentially scale up to quite high demands, but also they potentially scale down to 0. And as I mentioned, for me, that's where serverless shines. The fact that we're not paying for this infrastructure when we're not using it means that we save money. We don't need to bother our friends in data engineering and IT. We can do this stuff on our own without necessarily setting fire to our own credit cards. And crucially, we can go and have coffee and be relaxed while we're having coffee and not worry that the infrastructure is running because we've got an EC2 P2X large or something running that's stressing us out. So that's what it's good for. What is it not good for? If you talk to people who do like real software engineering, who do operations, they'll tell you all the things serverless is not good for. It's very easy to spend a lot of money on serverless, despite the fact that I've emphasized that it's cheap. In practice, because costs scale linearly with usage, at some point that, for very large use cases, that graph crosses the other graph of just buying the server. So you may want to think about that. But the use cases I'm focused on, these data science use cases, there's some things it's not good for. If you're familiar with MapReduce is often misused to describe algorithms that are map, shuffle, reduce. What that means, MapReduce is map the computation among many workers, and reduce means consolidate the results into, for example, a single number. So for that squaring example, reduce step would be either consolidating them into a list or maybe even taking the sum of the list, the sum of all the squares below 5 or something. More commonly, MapReduce in a data engineering context involves a shuffle step, which is when the workers communicate with each other. That you can't do out of the box with PyRen. You need to like hack it in, essentially, is an accurate description of it. And usually the way it's done is by writing intermediate results to S3. So at that point, you're having to worry about your infrastructure a lot more than you would if you were just using Spark, for example. By the same token, PyRen, with its focus on embarrassingly parallel stuff, is not a good fit for most linear algebra jobs where the matrices are interestingly sized. Most linear algebra computations, such as matrix inversion, are not embarrassingly parallel. Same reason, they involve interworker communication. You can break them apart so they become parallelizable, and that's what libraries like Dask do. PyRen doesn't know how to do that. It's just got this primitive map function. The PyRen folks are working on a library that, you know, it may not surprise you to learn is going to be called NumPyRen, which is going to know how to do that. But for now, at least, don't invert a 1 million by 1 million matrix using PyRen. It's also, I need to update this slide, this should say 15 minutes, 900 seconds. It's no good for atomic tasks that last longer than 900 seconds. I showed how you could accumulate small tasks up so they're above 20 seconds, but there's no way to, if there's no way to break down your task so it's below 15 minutes, you're stuck, basically. And then finally, I mentioned very briefly, these machines do not have GPUs, so they're no good for training neural networks generally, even if you could train them in under 15 minutes. So I want to sum up by referring back to the title of that paper I mentioned, which is a reminder you should check out if you get the chance. It was called Distributed Computing for the 99%. And what I understand by that is if you're one of the data science 1% who operates a company with a data engineering and IT support and plenty of financial support to run long-lived infrastructure, then you may not be the kind of user that the PyRen team, for example, have in mind. At those organizations, global consumption of this infrastructure certainly varies, but it probably never goes down to zero. It never even gets that small if they're doing a good job. And they may be operating at such a scale that it's cheaper to just buy the cluster as well. Serverless, in the sense that I presented it today and the Pyren folks are thinking, I don't think they're not the target market for them. Who is the target market is perhaps if you're operating independently and you want to do a fairly large-scale computation without dealing with Spark, things like that. Or you want to deploy a machine learning model in a way that can scale up very large, potentially if things go well, and then you can phone your friends in operations and they can deploy it for real. For that use case, or just for having some fun at home, taking the square of 6 numbers, if that's your idea of fun, then I think Pyren and Serverless is a great tool. That's it. Thank you very much. And we've got 5 minutes, right? Yeah.
Hi. Since Pyren works for AWS, is there anything for the other providers that is similar that you'd suggest?
So the reason why Pyren is targeted at AWS is kind of a grubby reason, which is AWS gave these folks at Berkeley free credits, basically on AWS. There's nothing technical to stop Pyren targeting the other serverless backends. Zappa's a slightly more interesting political story, and I'm kind of reluctant to get into it with the video on, but my understanding of the situation is Chalice, AWS's official serverless client, is obviously never going to support Google Cloud or Azure. It also is missing the cron feature that I actually used in Zappa. The folks who build Zappa are pretty adamant that the agnosticism of that tool is one of its selling points, and I would agree with them. In practice, when I last looked, it didn't actually support any of the other ones. It was just like, we could if we wanted to, we just haven't got around to it yet. And that was a while ago. I last looked like 9 months ago, and that situation may have changed. They clearly feel politically quite strongly about that. So when I said it's not just a case of SCPing your application between one or two of these things, that's true, but the basic premise, in the algorithmic sense, the alternatives to AWS Lambda are good fits for Pyren. I just think it's a case of no one's done the work yet. There's a huge amount of bookkeeping going on in the background that is just not fun code to write, I think. So, yeah.
So, would another potential use case, if I was a malicious actor, would be to use the distributed lambdas as independent asks? So, if Google limits my API, but I write 100 different API keys and I want to iterate through them through lambdas, will the AWS Lambda really independently do all of those? Or does that warmness kind of be like, oh, Google can see it's all the same, and I could tell these are all really coming from the same source?
I know Google will be able to see it all the same because I got blocked by NIPS. And the reason is they all come from inside the same data center, so they all present from the same subnet. They all have very similar IP addresses, so any well-configured website or API is going to figure out something's up. There are workarounds for that. People have written hacky scripts, not even with serverless in mind, but with either malicious or pragmatic, let's say, web scraping in mind, that iterate not just through API keys but IP addresses as well. If you have if you have you're in US West 1 and US East 2 or whatever, you can work around that. Serverless won't help you on its own with that though. No.
One comment on that: it's a very good way to use your AWS account.
It is. Yes. Yeah. It's.
They're very clear on no, you can't use.
Yeah, it's not designed for scraping. Yeah. And when I was writing this talk, I made a few mistakes writing the scraping code, and the bill at the end of that month was not small. Despite what I said in this talk, I got a $30 bill, whereas usually it's 30 cents. And that's just me messing up and finding after 10 minutes that I've messed up and just paying for endless 1,000 worker jobs. One more question, right at the back.
If you're at a mid-sized organization where, let's say, you're not in the 1%, but you're not at the point where you have your own AWS keys.
You're in the 5%.
Yeah.
Yeah. Top tax bracket still, but not like a billionaire.
Exactly.
Yeah, yeah.
Is which I feel like is most of us.
Most of us are, if we're honest.
How do you do accounting? When I request an EC2 instance, I'm not the one who. There's an IT team. How do you guys do accounting for this stuff?
This is one of the challenges of you're trying to anticipate usage that you don't necessarily know what it's going to be. And it's a feature, an engineering feature that serverless can scale up to arbitrary usage. But that's a feature that is going to make accounting extremely nervous. Like, what if this is a success? That would be a disaster from accounting's point of view. And so there's like a communication problem there of like, this is a good thing if this works out. And here I can tell you exactly what each user is going to cost us. Per user, is that worth it? The other thing to think about is, when do the lines cross? Like I mentioned that you can predict usage exactly based on number of users you've got because it's a linear relationship, whereas fixed infrastructure becomes cheaper at some point based on the number of users. And you can model when those two lines cross. And maybe that isn't something you and engineers should be doing. It's something the folks in finance should be thinking about, if you've got folks in finance who like EC2 instances. Yeah, that's a rough idea. Cool. That's it. Thank you very much. I'm around if you want to talk.
Thank you again, Mike.